Today we're doing 3.5, making connections with rational functions and equations. So by the end of today's lesson, you should be able to solve real-life problems involving rational functions, and you should be able to graph rational functions with holes. Okay, so a discontinuity is just a value at which a function becomes undefined. And so far you know two types of discontinuities, horizontal and vertical asymptotes. And another discontinuity is going to be this hole. And so we'll see how holes arise. So I could give you this example. Graph f of x equals x squared minus 2x minus 15 over x squared minus 9. Now, I won't normally ask you to graph a quadratic over a quadratic unless we can cancel a common factor and get it down to a linear factor over a linear factor. So let's see if this is factorable. This is going to be x minus 5 times x plus 2. Hello, 3. And this is x minus 3 times x plus 3. So you can see, not so easily, that there is this common factor of x plus 3. So I'm going to cancel that, and I'm going to end up with f of x equals x minus 5 over x minus 3, where we have that x cannot equal 3 or negative 3. This one, x equals 3, is a vertical asymptote, and because we canceled a common factor up and down, this one is a hole. So now I'm going to graph f of x equals x minus 5 over x minus 3, just like you learned how to in section 3.3. So we're going to find the four key features: the vertical asymptote, which we already did, that's x equals 3. The horizontal asymptote, which is the coefficient of the x's, remember, so that's f of x equals 1. We're going to find the x-intercept, which occurs where the numerator equals 0, so that's going to be x equals 5. And then we're going to find the y-intercept or f of x, we could use, doesn't matter, y equals the constants from the numerator and the denominator, so that's going to be 5/3. So this is the 0.50, this is the 0.05. Okay, so I've got my asymptotes all ready to go here, so that's x equals 3. So let me just change to a cursor here. So x equals 3. Oh dear. Let me just lock this. I think I will learn. Okay. So then we're going to move this to x equals 3. We're going to move this to y equals 1. And we're going to plot our point 50 to 3, 4, 5. And we're going to plot our point 0.5. So that's 1 2/3, which may be around here. Oh, this is nice because I have 1 point in each quadrant. So now I can just draw as best I can with this tool that I use. The branches, oops, that's approaching the asymptote. I'm going to put the equation on. I'm sorry, I should have. So this is going to be f of x equals, and I can't write x minus 5 over x minus 3. Maybe I'll stop and not put the equation on yet because I want to explain something first. And I'm going to go back and I'm going to extend this a little longer. So this is going to go. And again, it's very difficult. You know I can't touch that asymptote. I'm just approaching it. Okay, so this is the graph of x minus 5 over x minus 3, but that is not the graph we were asked to graph. We were asked to graph this function here, x squared minus 2x minus 15, and x over x squared minus 9. That one had a hole in it at x equals negative 3. So what we have to do is we have to figure out where that hole is. So I need to find, so for the hole, I need to find f of negative 3. And I can plug that in to this equation here because the hole is on this branch here. And so if I go ahead and put in negative 3 minus 5 over negative 3 minus 3, I get negative 8 over negative 6, which is, when I divide by 2 on top and bottom, positive 4/3. So I have a hole on my graph at negative 3 4/3. So I am going to go and draw in that hole. I am going to go to negative 1, negative 2, negative 3. I'm going to go up, and that should be at negative 4/3, which is negative 1 1/3. So I am going to very obviously, I'll even use a different color, show that hole in my graph, and I'm going to label that particular point. Okay, so I want you to always label the hole. So that's minus 3 4/3. I want you to label the other point that you found, the y-intercept, which was 0 5/3. And this one over here was 5, 0. And now I'm going to put my equation on, but I'm not putting this equation on because this graph has a hole in it. This is the graph of the quadratic over the quadratic. So that's what you're writing on your graph. Okay, so x squared minus 2x minus 15 over x squared minus 9. I just have neglected to label my asymptotes. Y equals 1 here, x equals 3, and I believe I've got everything else now. Okay? So that's graphing equations with holes. Sometimes when you cancel the factors, if you didn't start with a quadratic over a quadratic, if you started with, say, linear over a quadratic, you may end up with a reciprocal linear equation. Or if we started with a quadratic on the top, and a cubic on the top and a quadratic on the bottom, you may end up with if you had a cubic on the bottom, that would be okay, and one factor, a linear, on the top. When you cancel, you could get a reciprocal quadratic, which you do know how to graph. So rest assured, once you've canceled any factors, and there can be more than one factor, which means there would be more than one hole, you should be able to have a graph of either a linear over a linear, or a reciprocal linear, or a reciprocal quadratic, all of which you know how to graph. Okay? They'll just have holes in them. Alrighty, let's keep going here. This is a word problem, obviously. In order to create a saline solution, salt water with a concentration of 40 grams per liter is added at a rate of 500 liters per minute to a tank of water that initially contained 8,000 liters of pure water. The resulting concentration of the solution in the tank can be modeled by the function c of t equals 40t over 160 plus t, where c is the concentration in grams per liter and t is the time in minutes. Sketch a graph of this function. Okay, so this is a linear over a linear, and when we're graphing a linear over a linear, we need those 4 key pieces of information, right? We need the vertical asymptote, and that comes from division by 0, so our vertical asymptote is going to be t equals negative 160. That makes this 0. Our horizontal asymptote is going to be where we've got the coefficients of the t's, and so that's going to be c of t equals 40 over 1, so c of t equals 40. We want the t-intercept, we'll call it. That's the equivalent of the x-intercept, and that's going to occur where our numerator is equal to 0, so 40t has to equal 0, so t has to equal 0. And then our C of t intercept, better known as our y-intercept, occurs where we've got the constants in each of the numerator and denominator. So the constant here is 0, right? There's like a plus 0 here, and there's a constant of 160 here. So C of t is going to be equal to 0 over 160, which is 0. Okay. We should have enough information to graph this. Keep in mind this is a real life problem, and so we should be labeling the x and the y axes. So go back to your problem if you're not sure what your x and your y axes represent. In this case, t is your independent variable, and t was the time in minutes. Sorry, I'm just going to put an x-axis on here. So let's move that up. So let's make that the x-axis, which means I'll put time below that. So time in minutes, and this would be over here the concentration in grams per liter. Okay, so we know we have a vertical asymptote at t equals negative 160. Well, I know that's way the heck over here somewhere. I'll just draw it in anyway, but it's not pertinent to our question, but it helps me sort of define the area at which I will be graphing. I have to have a horizontal asymptote at C of t equals 50. And so, sorry, 50, what am I saying? 50, 40. And so I'm going to maybe go up by 5, so 5, 10, 15, 20, 25, 30, 35. There's 40. Anytime you change the scale and it's not 1, I expect you to indicate that. And you don't have to write it all in, but you do have to give me the first one. So this is 5, and then I would put in, you can just put in C of t equals 40 here. Okay? All right. I didn't change my x-axis. I'm still going to make that going up by 1 minute increments. Okay. So now I'm going to graph my points, and the only point that I have is the point 0, 0. That's okay. That's enough. I only need 1. And then I'm going to, we really don't know what the stretch is without coming up with some more points, but that's fine. So there's my graph. I'm going to put the equation on there, so it would be C of t equals 40t over 160 plus t. I've got the asymptote labeled, I've got my axes labeled, and I just need to put the label of 1 point on there. Okay, so I've sketched a graph of this function. Let's answer some questions related to that word problem. So we're going to determine algebraically how many minutes it will take the saline concentration to be 20 grams per liter. So that's, we're going to replace C of t with 20. The equation was 40t over 160 plus t. And let's identify the restriction. T cannot equal minus 160. We're going to cross multiply over 1. When we cross multiply, we get 40t equals 20 times 160 plus t. And we'll just isolate our variable. T is 160, therefore it will take 160 minutes to reach a concentration of 20 grams per liter. I could just, again, this is just more habit than anything, but we could just say T cannot equal negative 160, just so that we have sort of revisited that restriction to make sure this one's okay. All right, is there an upper limit to the concentration in the tank? Explain. Well, let's just go back and reread the question for a second. So it says they are creating a saline solution by adding salt water that has a concentration of 40 grams per liter to a tank at a particular rate. And the tank initially contains 8,000 liters of pure water. So regardless of the size of the tank, you're never ever going to have a concentration of 40 grams per liter because you started out with 8,000 liters of pure water that had no saline. So we know that we are going to approach a concentration of 40 grams per liter if we had a huge container. If we have a smaller one, it's not going to be 40 grams per liter, but it will start to get closer and closer as you put more water in. Okay, so I think that's what you should be explaining. You should not just be saying, oh, there's a horizontal asymptote of 40 grams per liter, or of 40. You should be talking about the sort of the context of the problem. So we could say, yes, there is an upper limit of 40 grams per liter. And you could say, in brackets, the horizontal asymptote. That's fine. But when I want you to explain, so maybe this is a two-point question, and that's the first part, yes, and what it is, but why? Since the tank contains 8,000 liters of pure water, and saline with a concentration of 40 grams per liter is being added to the tank, the concentration of water, or of saline, you could say, will never reach 40 grams per liter. However, it will approach 40 grams per liter depending on the size of the tank. Okay, so that's, it's a word problem. You want to refer to the context of the problem. Okay, what restrictions must be placed on the domain of C if the tank has a maximum capacity of 120,000 liters? I really think this is a confusing question in terms of the way it's worded. Do you mind scratching it out and putting in what is the domain and range of this problem if the tank has a maximum capacity of 120,000 liters? I think that's clearer. You're really just finding the domain and the range. So always think about the domain. You go back to the problem. You say, what is my independent variable in this particular example? And it was our t, so that's the time in minutes. So I like to just know very clearly what my independent and dependent variables are. And the range, the y's, are my concentration. And again, include the unit when you're sort of revising or revisiting it. Concentration was grams per liter. Okay, so if my tank is 120,000 liters, then, and I started with 8,000 liters of pure water in the tank, then the maximum amount of saline solution that I can add is the difference between the two, obviously. Okay, and the minimum amount that I can add is 0 liters. What if my hose breaks or something? Okay, so, but that's not what we're being asked for in the domain. We're being asked for the time. So if you go back to the question, it said that the water was being added at a rate of 500 liters per minute. So we want to know the minimum time, and if we have a rate of 500 liters per minute and we're adding 0 liters at 500 liters per minute, then our time, well, I shouldn't put the units on, but they're inferred. The time is going to be equal to 0 minutes. It's going to take you 0 minutes to add 0 liters. That makes a lot of sense. The maximum time, again, it's going to be the number of liters that you're putting in divided by the rate. So the maximum time is going to be, and I'm squished here, so it's a bit of a problem here. I'm just going to come down here. The maximum time is going to be 120,000 liters. That's the max capacity, minus that 8,000 liters, right? So you're only really able to put in 112,000 liters at a rate of 500 liters per minute. So when you add, or when you subtract that and do the division, you end up with, I'm going by memory, it was 224 minutes, I believe. Okay, so our domain, algebraically, in interval notation, would be 0 to 224. The minimum amount of time would be 0, the max 224. Can we have a situation where we're not adding any water, or saline, sorry? Of course, we'll have a square bracket. Can we actually get to 224 minutes? Sure, it'll be full at that point, but it's all good. And then the range, remember, is a dependent variable, so the range depends on the domain, and so we are going to figure out what our concentration would be if we added 0 saline. And obviously if we added 0 saline, there would be, the concentration would be 0 because we started with pure water, which had no salt in it, right? So we are going to, that one was easy, and really you can, I just don't have the room, I'm sorry, you can do this by just substituting in 0 for your equation. So you had C of t equals, I'm just going to steal some space from down here, 160 plus t, so C of 0 is equal to 40 times 0 over 160 plus 0. Well, 40 times 0 makes the whole thing 0, right? So C of 0 equals 0. We're going to do the same thing for 224 minutes. So when you have, after 224 minutes, your concentration would be 40 times 224 over 160 plus 224, which is, I don't know. Well, you know what? I do know that the answer, I believe, because I'm going by memory and I don't have a calculator right here, it was about 23.3 grams per liter. Okay, and this is minute. This is grams per liter. So if we were coming up with our maximum possible concentration, it would be 23.3, and we can get there. Okay, this isn't the asymptote. It's not like it's 40. We can get there, so we have a square bracket as well there. Okay. I think I'm just going to let you leave it in interval notation rather than the word have the words for that one. So I think that's sufficient for a solution there without just putting a concluding sentence in. All right, determine the equation of a rational function with a hole
at x equals 3, a vertical asymptote at x equals negative 2, and a horizontal asymptote at y equals 4. All right, let's just get rid of this. Okay, so you know, we're just going to sort of build the equation from the information. And so you know that if you have a horizontal asymptote at y equals 4, then this cannot be a reciprocal function. It can't be a reciprocal linear or reciprocal quadratic, because they all have horizontal asymptotes at y equals 0. So we know that this is probably going to have a linear factor. Well, it definitely has a linear factor that we are going to cancel. And so we would start with f of x equals x minus 3. So that's the linear factor that gets canceled that creates the whole. And then what else do we have to include then? We still have more things to think about. It has a vertical asymptote at x equals negative 2. Vertical asymptotes arise from division by 0, so this would be x plus 2 on the bottom. And it says a horizontal asymptote at y equals 4. And remember, the horizontal asymptote arises from the coefficients of the x's. And if this one has been canceled, then you're really only considering the coefficient of this one. So you would put 4x here. So 4 over 1 gives you that y equals 4. This could have been really any factor like this. Okay? And I would not put a squared in there. I mean, I would just leave it as a linear factor in the numerator. So it could have had any plus or minus value here, because it didn't talk about the y-intercept, so you didn't matter. And it also didn't talk about the x-intercept. Okay? Some of them will get a little more complicated than this, but this is a viable solution in this case. Okay, so you're just building the equation. It's not that bad. All right, that's it for the lesson. Thanks for listening.